Questions? Does anybody have homework stuff you want to talk about? Mary, you want to lead off? 23? Sure.
Yes. No. You can use because it goes from close to high. It can go from -4 to -9. Yeah, you have to start really, it says in the note somewhere that it says always play a small one first.
All right. So the directions here are to, let me just double check. Eliminate the parameter and find the domain and range. So what we'll do is we'll start with our x equation. And we'll solve that for t. So I'll divide both sides by -1/2. Square root both sides. Plug that back into here. Now, oh, sorry. Now we probably, yeah, that's fine. That's fine. I think in the answer key, we probably rationalized the denominator and did a little bit of extra gobbledygook, but whatever. This is fine. Now to do the domain is coming from the x coordinate. So what I notice is that this is a quadratic function, the equation for x. I know that a quadratic function is sometimes increasing and then sometimes decreasing. So in addition to the endpoints of the interval, -4 and 3, I also need to worry about where the function changes from increasing to decreasing or decreasing to increasing. Now for quadratic, that's just going to be one place at the vertex. So to find the x coordinate for the vertex, I can do -b/2a. Now in this case, that's really easy because the b is 0, so just 0. So there's 3 values I need to check. I need to check x of -4, x of 0, and x of 3. So let's see, -4 gives me -32, x of 0 is 0, and x of 3 is -18. So my domain then should be going from the smallest, -32, to the biggest, 0. And since these were brackets, I know that these guys are brackets. And I guess there's one thing I should have checked before I started doing this. What's that? Well, I need to make sure that 0 is inside the interval, right? Just because the vertex is there, I need to make sure it's actually inside the interval before I use it. I didn't make mention of that, I just did it. Should go back and make mention that it was, we do have to check that. Now to do the range, we're just going to care about the y coordinate. Here I notice the function for y is linear, so that's always increasing or always decreasing. So I don't care about anything other than the endpoints. So that's going to be -12 plus 4, that's -8. And then 9 plus 4, that's 13. So there's my range. It's just small to big. Nothing more to do there. Is that okay?
You go to the left a little bit, I just want to.
How about that? Knowles?
So the only thing that changes when it's a quadratic is you just find the x-point of the vertex and plug that in.
Yeah.
What if the y had been a quadratic too?
Then I have to do that for the range also.
Okay.
What if it was a cubic? I wouldn't give it to you because it's not easy to find the extrema of a polynomial that's not a quadratic without a calculator, without calculus. So if you take AP Calc next year, you'll learn how to do that. And it's not terribly difficult to do, but it's probably a month of like background before you can understand like what it is that you're doing to be able to do that. But
So basically, you take your x, you solve for t, and you plug that into the y equation. And how does that y equation help you?
it doesn't.
So it's just
But
solve for
the
it.
direction said to eliminate the parameter and then find the domain and range of the resulting function.
Okay, so you're just going to take the regular equation, y x.
Correct.
For domain range, you take that.
You go back to the parametric.
Okay.
You have to be using the parametric because the domain for that has to match the new domain, or match the domain for the function you just written.
Yeah. So for the range, which numbers do you use to y -4, 3?
I'm just plugging it into my equation for y. Right, that's y of t. That's like an equation. Where y is a function of t.
Oh,
So I just took those values of t and plugged them into the t for that
Is that the
equation.
same thing you're doing for x?
Yeah. So I'm just using my equation for x, which again is like an x of t. It's x is a function of t. Does that feel okay?
Yeah.
These are good questions, guys. Good clarifications, right? Like it's important you understand the notation, understand like the process, these high level, like in general, what are we doing here questions are good ones. Happy to do, we have lots of time, happy to do more. Kendall? 30? Yeah. Let's grab that. So here we want the parameterization of a line through a pair of points. So for something like this, what I'm going to do is I'm just going to use the, bless you. I'm going to write the vector equation for the line like I would have in chapter 8. So R naught is just my point vector, so I could use 4, -2, or I could use -8, 3. It doesn't matter which one. I'm going to choose to use this one. And then V is my direction vector. That could be 4 minus -8, -2 minus 3. Or you could reverse it. It doesn't matter. I'm going to choose to use this one. So I have R is equal to 4 -2 plus 12 -5 t. If I go and do my vector operations, I do my scalar multiplication, vector addition, I'd have 12t plus 4 as my x component and -5t minus 2 as my y component. And that's all I need now to write my parametric equation. So 12t plus 4 is going to be my x equation. and negative 5t minus 2 would be my y equation. And because we're dealing with a line is infinitely long, so the interval that I'm going to be using that parametric equation over is just going to be all real numbers. Jean-Paul? 43. Kendall, are you happy with what I did there, though? Yeah. Okay, sure. Okay, oops. All right. So Jake hits a baseball when it's 4 feet above the ground with initial velocity of 120 feet per second. The ball leaves the bat at a 30-degree angle with the horizontal and heads towards a 30-foot fence that is exactly 350 feet from home plate. Write a parametric equation to model the flight of the ball. Okay. So my parametric equation for x should be initial velocity times cosine of the angle, t. My y equation is negative 16t squared plus initial velocity times sine of the angle, t, plus the initial height. Yes. John Paul?
Can we get the formulas on?
Nope. Okay. Part B says, if no fence or any other obstacles were present, find the distance the ball would travel when it first hits the ground. So it's asking like how far is it going to go? That's asking for an x value. And to find that x, what we're going to do is we're going to solve our equation for y in terms of t, and then use that value of t to plug back into x to get the distance. So what value of y are we interested in? That's right. So I'm just going to take y of t and set it equal to 0. We'll use the quadratic equation to solve this. And now I have to be careful. I have to make sure I put a parenthesis around that 120 sine 30 before I do the squared, or else it's just going to square the sine 30 part and not the 120 also. So I do have to be a little bit careful there. Otherwise, all I'm doing is just filling in the quadratic equation, or quadratic formula, excuse me. So I got a negative value there for the plus. That doesn't seem like the answer I'm looking for, right? Because what we're solving for is a time, like how long the ball's in the air. So let's just change it to the minus, because it could be plus or minus. So I got about 3.82. So that sounds reasonable for the amount of time the baseball's in the air. So I'm just going to plug that 3.82 in for the t for x and figure out what that is. So 120 cosine 30 times that answer. So 396.5 feet. And then part C asks, will the ball clear the fence? If so, by how many feet? If not, will it be catchable, i.e. less than 10 feet from the ground? So here, if we want to know if the ball clears the fence, we need to know the height of the ball, right? When x is what value? 350. So I'm going to go ahead and take my equation for x, set that equal to 350, and then solve for t. That's just a linear equation, so I can just divide both sides by 120 cosine 30. I'll type that into my calculator. The number I'm expecting should be less than 3.8, right? Because it should be, I would expect the ball to be going past the fence if the fence isn't there. So 3.68, that sounds pretty good to me. So then I'll do y of 3.68. And see what we get there, and we'll compare that to the, 30-foot fence. Good gravy, that's a tall fence. All right, so we have negative 16 times. Oh, yeah, cool, thank you. That's, yeah, I'm going to use the answer command. I'll fix it on the sheet in just a second. But, yeah. I don't know how I got to that one. Did you ever, your brain just start doing whatever it feels like and for no good reason? That just happened to me. All right, so I'm plugging that t in for y. I get 24.6. Now that's less than or equal to 30 feet. So not a home run. Maybe. But it's also bigger than 10 feet, so not catchable. So that's probably bouncing off the wall for a double or something.
Maybe a single. Maybe a triple. No, if that's Christian can see where the bounce is gonna go, and then go straight to second, get him out.
Okay.
It doesn't count as an out if you catch it off.
No. She you know where the ball is gonna bounce off the wall. You get the ball in the outfield, you go straight to second, get him out. It's like the perfect that one's a shot.
John Paul, you happy with what we did there, though?
Yes.
Okay. CJ, you wanted 39, you said? Okay. All right, so let's just say we did 49 or 37 here, just as an example. If we did this, this should have been pretty easy. We just did 5 cosine t and then 5 sine t, right? That'll be a circle with radius 5 centered at the origin. So if we're doing 39, let's ignore the center for a moment and just want our radius to be 6. I would do this, right? That'll give me a circle with radius 6 centered at the origin. Cool? Yeah. Now, if I want that circle now that was at the origin to be translated left 1 and up 2, so its center is now at that new point, what type of geometric transformation is that? That's a translation. Very good. If I want to take all the points at the circle centered at 0 and move them all left 1 unit, how do I do that? What do I change to the points? You're great. And what do you do to the x value? Subtract 1. So what am I going to do here? Subtract 1. And if I want to make the y values go up 2, I'm going to just add 2 to the y's, and that ought to do it. Yep. And it's one of these that it's like, it's just easier to talk it through than like to do anything algebraic. It's just like, oh yeah, sure. Yeah, it makes sense. All right. Others, happy to do some more if you guys got more questions. Lily, we talked it a minute during CT. Those are okay? Okay. I'm just figuring I'm following up. Elena.
17.
Sure.
It just has different subjects.
All right. So again, first thing I'm going to do is eliminate the parameter. So I'm going to take my equation for x, solve that equation for t, and then plug that equation into y. So if I have x minus 2 squared, how do I simplify that? FOIL, very good. Very tempting to just distribute your exponents. Do not do that. Exponents don't distribute. And then we'll distribute the 2 through and combine our like terms. So far, so good?
Yeah.
Okay. The domain then is linked to the x equation. So this x equation is a function in terms of t. Specifically, it's a linear function in terms of t. If the domain of that linear function, or the inputs for that linear function can be any real number, the outputs are going to also be any real number, right? So nothing really to do there. The range is going to come from the y coordinate, or the y function. Shh. I recognize the y equation is a quadratic. Now, a quadratic equation, the outputs are not going to be all real numbers, even if the inputs are all real numbers. It's going to either go from negative infinity up to the vertex, or it'll go from the vertex up to positive infinity, right? The range will be one of those two. I can tell by looking at it that this is a parabola that opens up because the leading coefficient is positive, so it's going to be the vertex to positive infinity. I just need to figure out what the y-coordinate of the vertex is. So to figure out the vertex, I solve t using negative b over 2a. So that's just going to be 0. And then y of 0 is 3. So my range should go from 3 to positive infinity. Does that feel okay? Yeah. The 3 gets a bracket because clearly 3 is an output of y. I've just shown it. That's why it's getting a bracket rather than a parenthesis. Joe?
How do you know it goes to? Oh, because it opens up.
Yep.
So, just to like clarify, so if the for t, if it wasn't negative infinity, positive infinity, like let's say it was like 3, negative 3, 5. So you would just plug in
negative 3, 0, and 5, and go from lowest to biggest.
That's just for the range.
Because it's a quadratic.
That's what we got for the vertex. But for domain, you'd only make it 3 and 5.
Because it's linear. If the domain was quadratic, then I would have to check the endpoints and the vertex.
Right.
But cool. And really, even if it's quadratic, you don't really have to check both endpoints if you're clever. But I would just check them all. It just saves you from having, like, thinking about it the wrong way. It just never doesn't take much to evaluate them, so it's fine. Allie, I don't think we did 44 yet. I did 43, which is almost exactly the same problem, though. Okay.
Could you just go over like the process actually behind the pyramid?
Yeah, you just want to talk through it?
Yeah.
Okay. So for part A, I write my parametric. So again, that's initial velocity times cosine of the angle, and then a t. For y, it's negative 16 t squared plus the initial velocity times sine of the angle, t, and then the initial height. For part B, where it says we're just looking at about how long this, or the distance the ball would travel before it hits the ground. So what we're going to do is we're going to take y of t, set it equal to 0, and solve that for t. And then we're going to plug that t into x of t. And that's going to be our answer. For part C, it says, will the ball clear the fence? So here I'm going to set x of t equal to the distance the fence is from the home plate. And I'm going to solve that for t. And then I'm going to plug that t into y of t and compare that to the height of the fence and catchable, which was 10 feet, I think. So if it's between 10 and the height of the fence, it's not catchable, but it's not a home run. If it's over the fence height, it's a home run. If it's under 10 feet, it was catchable. But that's basically all I'm doing. It's just kind of comparing that number. Does that feel okay? Do you want to see details? Or did I? This is what I thought you were asking, right? This is just like the high level process of like what we did.
Like, for B when it's y, do I literally do like write out y and it equals?
Yeah, and you're setting that thing equal to 0. So you use the quadratic formula to solve that, right? Like negative b plus or minus square root b squared minus 4ac all over 2a. That was fast. But you know it, I hope, right? So that's all you're doing. Now there's 2 answers to that, right? How do you know which one is the one you want? It'll be the positive one. The other one will be negative, which is like, I know negative time, because t is time here, right? That's like the lurking parameter. And negative time is, that's bonkers. If we're talking about like how long a baseball's in the air, it's not negative time. Does that feel okay? So whatever that answer is, then you're going to plug into the t in the x equation, and that'll give you the distance. And we'd expect it to be somewhere in the neighborhood of, like 385 or whatever, right? I'd expect it to be past the fence, because even if it hits the fence, we're assuming there's no obstruction. I'd expect it probably going that far at least. To give you an idea of like, oh, I got 86. Well, that's not right.
Yeah.
Right? Or I got 10,042. It's like, well, that's a problem. Is that any better?
Yeah.
Okay. Diego.
46, it takes that problem and adds wind.
Yeah,
So you add that to velocity.
yeah, that's exactly the right idea. Let's
Going in the same direction.
right. So it says 46 says in question 44, the exact moment that Matt hits the baseball, there's a gust of wind that acts in the same horizontal direction of the ball at the speed of 6 feet per second. So how does this change things? Well, a horizontal wind is not going to change the y at all. That'll stay the same. What was that? It was 115, wasn't it? Yeah. But it will change the x. So the initial speed of the ball was 115, but we also have that oops, that's supposed to be a sign down there. But then we have that little wind gust on it. And that's the setup. Yeah. So that just becomes 121. And then it's the same problem or process after.
Do you not sub into 6 anywhere else?
Correct. Just because the wind is horizontal, so it's not going to affect the vertical component unless you had like a downs, like some kind of like wind blowing down, like a tornado or something.
And then for B and C, we just do those the same way with the new number.
Exactly. Yeah. Yep. And in fact, for part B, is the ball going to still be in the air the same amount of time?
No.
Yeah.
Yeah.
Yeah. So, because the y doesn't change, right? Solving y is going to be the exact same problem. It'll go further because the wind will push it a little bit further, but the ball will still be in the air the same amount of time. It's just going to go a little farther. $47.
When it hits the ground, so y is 0, you get that, you get t of y 0, where the x is, and then to get to the wall, you set x to 385, that's on the wall, get it to t, and then get the t, get the y is above the wall. If it's 10 feet or below,
All right. So let's look at 47. Sure. So stop talking, please. So it says you're standing 15 feet from the front of an 18-inch diameter circular target that's laying on the ground. Now, I'm going to convert that 18 inches into feet. It says, and then it tells you throw this thing and you're asking if it hits the target, right? So let's write our equation. So initial velocity is 30. Angle of release is 70. That's a big arcer, but that's not surprising. Back in the day, this was an actual game that they sold called Lawn Darts. But I think they stopped selling it because too many people that were playing it while drinking got like impaled by the other person throwing the long dart because they weren't really paying attention. And Yeah, you probably, if you have a grandparent, they might still have them laying around. Yeah. All right. So the goal here, what we want to find is we throw this lawn dart and we want to find out like how far did it go. We want to see if it's between 15 feet and 16.5 is going to be a hit, right? So what I'm going to do is I'm just going to take my y of t, set it equal to 0 to get my value of t, and I'll plug that into my x of t to figure out what that is. And if that number is between 15 and 16.5, yay! If not, boo! Yeah, I just need to find that value for t. So solving a quadratic, exactly right. So I'm just going to type this into my calculator rather than write it down. And actually, I'm going to just skip straight to the one that I know works. Hey, while I'm doing this, just as a reminder, what mode should my calculator be in? Yeah, all degrees on these. So 1.92 is my value for t. And I get, when I plug that back in, I get 19.74. That's a miss.
I feel like overshooting is better than
Kendall, does that feel okay?
Where did you plug that in?
X.
Oh, so you just plug it into the T.
Exactly. Yep. CJ. What's up? Number 3? Yeah. So it just says use your calculator to graph the yada yada yada.
Oh, it's because
So I'm going to go ahead and put this into parametric mode and into radian mode. I know it should be in radian mode for this because it tells me the interval is involving pi's. So I have 2 cosine t plus 2 cosine t squared. And then I have 2 sine t plus sine 2t. And if I think about this, the maximum output for cosine is 1. So the biggest the x could be is 4. So I'll make my x max maybe 5. And the same thing, if I think about the biggest output this can have is 0, and this is -1. So that's going to be -2. So I'll maybe make that -3. Oops. But not my t's. That was for my x's. Sorry. That was 2 pi, and that one was -2 pi. And then the y's, biggest output sine can have is 1, so that's 2, or so it's 2 plus 1, so 3 is the biggest. Can we stop talking over top of me, please? Thank you. The smallest output sine can have is -1, so that's like -3. So that's probably a pretty good window. So I do that, and I get that little sideways heart shape or whatever.
I don't have like the keys on my calculator.
It's because you're not in parametric mode. So you got to put your mode into parametric. And then you should, if you go back to the y equals, it'll have an x a t and a y a t equation for you. Cool? Yeah, no problem, Mom. Okay. What do we have left here? Okay, good. All right, let's do 10.3, and then we'll stop and do the quiz. So 10.3, we're gonna change gears here. We've kind of done talking about what do I want to say? The parametric stuff. The second half of this chapter, we're going to be talking about polar things. Now, the way we graph a polar function is decidedly different than the way we graph like parametric. In parametric, we didn't talk about how to plot points because you're just plotting on an XY axis still. Like the plotting is still the same. This is a decidedly different process for a polar function. So let's start by just defining what we mean by like a polar point. So we say a point in the polar coordinate system is defined in the general form of r comma theta, where r represents the point's distance from the origin, and theta is the measure of the angle that gives a terminal side for the point's direction. What does this r comma theta kind of sound like based on that definition? A vector. That's exactly right. That's all this basically is talking about a vector. So the way we're going to plot this when we plot a point in the polar coordinate system is our graph paper is going to look like this, where each circle represents a circle of radius 1, 2, 3, etc. And each of these straight lines is like, this is a 30-degree angle, 60, 90, 120, 150, 180. Or if you prefer to use radians, it's pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, etc. Is that okay? So let's talk about how we plot those things, or plot points then, on that space, right? So I'm going to do a little color coding here. All right. So what I do is I'm going to start by drawing the angle in. So 0, 30, 60, 90, 120 is this line here. Everybody's okay with that? And then from that line, I count 1, 2, 3. There's my point. Everybody feels okay with that? Not a big deal. We'll go to the next one. Oops, I was supposed to color code those, right? Dum-dum. All right. Pi over 3 is the same as 60 degrees. Remember, if you are not sure, you can always just multiply those by 180 over pi to convert them back into degrees. Or that's the same thing as 2/6, right? 2 pi over 6, so it's just 1 pi over 6, 2 pi over 6. But here, notice that I have a negative 2. What do I do with a negative? Well, instead of using the part that I've highlighted, I just kind of take the other side of that same line, and then I'll count 1, 2. That's all. No big deal there, right? Let's do the next one. So negative 100. Negatives are going clockwise. So 0, negative 30, negative 60, negative 90. So negative 100 is going to be like in there somewhere, right? Okay. Oh, but then my R is negative, so I actually need to flip it onto the other side. So it really would be over there. And then I just count 1 unit up. So it'd be like there. Does everybody feel okay there? All right. So just hypothetically, what if I wanted to plot the point negative 1 comma 260? Where would that lie? It's the same, in fact, it's not right about, it's the exact same location as the orange point, right? Why is that?
Because they're co-terminal.
Good, negative 100 and positive 260 are coterminal angles. They're the same direction, so they're going to end up in the same spot. What if we had, say, if I did 1 comma 80? That's 80 degrees. It's going to be the same spot, right? So what do we notice straight away about these polar coordinate points versus like our rectangular coordinate points? Big difference is the polar coordinate points are not unique, right? There's lots of different ways. In fact, there's infinitely many ways to represent one point. Let's collect those infinitely many ways into like a definition, right? So what do we have here? Given a point r comma theta in the polar coordinate system, any other point that coincides or is in the same place must be of the form same radius, but an angle coterminal to it. That's like what we did up here. Or opposite radius. We've added pi or 180, and then anything coterminal to that. That's like what we did here. And then we have two different versions, whether you're doing it in degrees or radians, right? Let's do a specific numeric example where we start with a point and we find all the coinciding points to that. So I'll start first with the yellow piece where I have just the point, the r stays the same, and I just need everything coterminal to it. So I just tack on the 2 pi n. Or I'll take the opposite radius, and then I'll have to take my angle and add pi or 180 to it. That gives me 11 pi, pi over 5, 6. And then everything coterminal to that. And b, again, r stays the same. Everything coterminal to it. or the r is opposite. We'll take our angle, add 180 to it, and then take everything, oops, not 2 pi n, dum-dum. We're in degrees, that should be 360. Is that okay? Just a formula, basically, right? Okay. So we have these two coordinate systems now. We have rectangular and polar. The next thing you want to do is convert between the polar coordinate system and the rectangular coordinate system. So I have some point in the polar coordinate system, r comma theta. I can calculate my x by doing r cosine theta and my y by r sine theta. If I have some point in the rectangular coordinate system xy, I can calculate my angle r, or I'm sorry, my length r squared just by doing, or the square of my length by doing x squared plus y squared. And I can find the tan of my angle by just doing y over x. Why does that work? Oops, that's, why did it, just put it here then, fine, be a pain. So if this is my r and that's my theta, to find x, well, that's just r times cosine theta. To find y, that's just r times sine theta. If I have x and y and I want to find r, well, the Pythagorean theorem holds, right? So I can find r squared that way. And to find that theta, well, I know tan theta is going to hold, right? So let's do 2 quick examples, converting between the two, and then we're done with this section. And that's all we're going to do today with polar stuff. So let's say we want to convert -3, 148 to rectangular coordinates. Well, I just use the formulas that I wrote above. And those formulas turn out to be like really quite useful. We'll use them a lot. So those are ones that you'll want to probably remember as long as we're on the topic. I just was in there changing back to degree mode here real quick. How did I know that I need to be in degree mode? Yeah, the angle is written in degrees. So I get 254 and then -159. So that's my rectangular coordinate. No big deal, right? Pretty stinking easy. What does this remind you of?
Bearing.
Yeah, exactly right. Like those bearing problems, like when you have to resolve a vector into component form. That's exactly the same process. This is why I think second semester is so much easier, is because when you get a new thing, it turns out not to be a new thing. You're just using the same tool that you used before, which is really kind of fun. So here we're going to convert a rectangular coordinate into a polar. So I get just the Pythagorean theorem. So r is going to be plus or minus the square root of 13. Which one do you suppose I want to use? Does it matter first? Not really, right? You can write the correct answer using either one. But which one are we going to choose?
Plus.
Yeah. Always pick the positive. It just makes life easier to do that, because then you don't have to worry about doing the flip for the angle or whatever. It just makes it easier. Okay? And now, if I think about it, what am I looking for after this? If I have that point, negative 3, 2, I have like that point. I'm looking for this angle. Boy, this looks a lot like a first semester problem, doesn't it? So I know that that angle is going to be 180 minus phi, where this is my phi. And that phi is going to be the tan inverse of the absolute value of y over x. So that's just going to come out to, when I type that all into my calculator, about 146.3 degrees. So there's my rectangular coordinate. Isn't this lovely that it's like this is nothing new? It's just stuff we've already done. Yeah, excellent is my opinion as well. All right, at this point, you guys should be able to do now 49 through 62.